Download this code from codegive.com, link in the description below. Failure testing at Netflix, a deep dive with code examples. Netflix is renowned for its robust and resilient cloud infrastructure. A cornerstone of this resilience is their commitment to failure testing. They pioneered and popularized techniques like chaos engineering, allowing them to proactively identify weaknesses in their systems before real-world failures impact users. This tutorial will delve into the principles behind Netflix's approach to failure testing, explore their tools and methodologies, and provide practical code examples to help you implement similar strategies in your own applications. Why failure testing? The traditional approach to reliability focuses heavily on preventing failures. However, in complex, distributed systems like Netflix's, failures are inevitable. Ignoring this reality is a recipe for disaster. Failure testing embraces this inevitability and aims to proactively identify weaknesses, discover vulnerabilities and single points of failure before they cause actual outages. Improves system resilience, strengthen the system's ability to gracefully handle failures and recover quickly. Increase confidence in the system, gain assurance that the system will perform reliably under various failure scenarios. Foster a culture of resilience, encourage engineers to think about failure scenarios during development and operation. Reduce mean time to recovery, MTTR, develop and test procedures for faster incident resolution. 2. Key principles and concepts, chaos engineering, the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. This isn't random chaos, it's carefully planned and controlled experimentation. Steady state, define a baseline of normal system behavior. This could include metrics like latency, error rate, throughput, and CPU utilization. The goal of failure testing is to ensure the steady state remains within acceptable bounds during and after the experiment. Hypothesis-driven testing, before introducing a failure, form a hypothesis about how the system should behave. This forces you to think critically about the potential impact and how it aligns with the system's design. Controlled experiments, introduce failures in a controlled and isolated manner. Start with small-scale experiments and gradually increase the scope and severity of the failures. Automated monitoring and alerting, set up comprehensive monitoring and alerting to detect anomalies and deviations from the steady state during the experiment. Automated rollback, implement automated rollback mechanisms to quickly revert to a stable state if the experiment reveals unexpected and critical issues. Documentation and analysis, thoroughly document the experiment, including the hypothesis, failure scenario, results, and any actions taken. Analyze the results to identify areas for improvement. 3. Netflix's tools and methodologies, Netflix has developed several tools and methodologies to facilitate failure testing. While many of these are internal, they've open-sourced some of them and inspired the development of other tools. Here's a look at some key aspects. Chaos Monkey, the original and most famous chaos engineering tool. It randomly terminates instances in production to ensure that services can survive instance failures. Simian Army, a suite of chaos engineering tools that includes Chaos Monkey, for instance termination, Latency Monkey, for introducing latency, Doctor Monkey, for detecting unhealthy instances, and Conformity Monkey, for enforcing security and compliance. FID, failure injection testing, a more recent platform that allows for more sophisticated and targeted failure injections. Fit enables engineers to inject failures at different levels of the stack, including network, disk, and CPU. Spinnaker Netflix's open-source continuous delivery platform, which is often used to automate the deployment and rollback of applications during failure testing. Monitoring and alerting Netflix relies heavily on comprehensive monitoring and alerting systems to track system behavior and detect anomalies during failure experiments. Tools like Atlas, Prometheus, and Grafana are frequently used for this purpose. 4. Implementing failure testing, practical examples with code. Let's explore how to implement failure testing in a simulated environment. We'll focus on a simple microservice architecture and demonstrate a few common failure injection techniques. The code examples will use Python, but the concepts can be applied to other languages and platforms. Setting up a simple microservice environment *. Imagine you have two simple microservices. *service _ a front-end service that receives requests from users. *service _ a back-end service that provides data to service _a. We'll use Flask to create these services. Explanation *. Service _a.py *. Exposes an endpoint /hello. Makes a request to service _b to retrieve data. Handles potential requests. Exceptions. Request exception, connection errors, timeouts, etc., and returns an error response if service _b is unavailable. Uses the service _b URL environment variable to define the URL for service _b. This allows for easy configuration in different environments. Service _b.py exposes an endpoint /data. Simulates some work by sleeping for a random amount of time, introducing artificial latency. Returns a JSON response with a random integer. To run these services *1 save the code as service _a.py and service _b.py. 2 make sure you have Flask and requests installed, pip install Flask requests. 3 open 2 terminals. 4 in the first terminal, run, Python service _a.py. 5 in the second terminal, run, Python service _b.py. 6 access http://localhost 5000/hello in your browser. You should see a response from service _a with data from service _b. Failure injection techniques and code examples *. Now, let's introduce some failures to see how our system behaves. 1. Instance termination, simulating chaos monkey. The simplest form of failure injection is to simulate an instance failure by stopping service _b. Experiment terminate the service _b process. Hypothesis service _a should handle the error gracefully and return a 500 error to the user. Steps 1. Stop the service _b.py process, example by pressing Ctrl+C in the terminal. 2. Access http://localhost 5000/hello in your browser. 3. Observe that service _a returns a 500 error with a message failed to connect to service B. Verification the code in service _a catches the requests.exceptions. Request exception and returns an appropriate error response, confirming our hypothesis. 2. Introducing network latency, simulating latency monkey. We can simulate network latency to observe how it affects our system. Experiment introduce latency between service _a and service _b. Hypothesis the latency of the /hello endpoint in service _a will increase. Method we can use a tool like TC, Traffic control, on Linux to introduce latency. This requires root privileges. A simpler, though less precise, method is to introduce a delay within service_b.py. Steps 1. Modify service_b.py as shown above. 2. Restart service_b.py, example Python service_b.py. 3. Access http://localhost 5000/hello in your browser. 4. Observe the increased response time. You can use your browser's developer tools, network tab, to measure the latency. 5. To control the latency value, export it before running the script. Latency_ms equals 1000 Python service_b.py will introduce up to 1 second of latency. Verification the response time increases, confirming that the injected latency is affecting the system. This highlights the importance of setting appropriate timeouts in service_a when communicating with service_b. 3. Introducing error codes, simulating faulty logic. We can simulate service_b returning error codes, example 500 internal server error. Experiment service_b randomly returns a 500 error. Hypothesis service_a should handle the error and return a 500 error to the user. Code, modified service_b.py. Steps 1. Modify service_b.py as shown above. 2. Restart service_b.py. 3. Access http://localhost 5000/hello multiple times. 4. You'll observe that sometimes service_a returns a successful response, and sometimes it returns a 500 error. Verification the code in service_a correctly propagates the error received from service_b, ensuring that errors are not masked. This emphasizes the importance of error handling and propagation in distributed systems. 4. Resource exhaustion, simulating CPU or memory pressure. Simulating resource exhaustion, example CPU or memory pressure, is more challenging but can be done using stress testing tools. On Linux, stress is a common tool. For these examples, we'll introduce a synthetic CPU load. Experiment introduce CPU load on the machine running service_b. Hypothesis the response time of service_b will increase, and potentially service_a will experience timeouts. Code, modified service_b.py. Steps 1. Modify service_b.py as shown above. 2. Restart service_b.py. 3. Access http://localhost 5000/hello multiple times. 4. Monitor the CPU usage on the machine running service_b, example using top on Linux. 5. Observe the increased response time and potentially timeouts in service_a. Verification the increased response time confirms that CPU load is affecting the system. This highlights the importance of monitoring resource utilization and auto-scaling based on load. See automation and monitoring *. These examples are manual. To make failure testing truly effective, it needs to be automated and integrated with monitoring systems. Here's a brief outline of how to approach this. Automation *. Use scripting languages, Python, Bash, etc., to automate the failure injection steps. Integrate with CI/CD pipelines to run failure tests as part of the build and deployment process. Use configuration management tools, Ansible, Terraform, etc., to provision and manage test environments. Monitoring *. Use metrics libraries, example Prometheus client for Python, to expose key metrics from your services, latency, error rate, CPU utilization, memory usage, etc. Configure monitoring and alerting systems, example Prometheus, Grafana, to track these metrics and trigger alerts when anomalies are detected. Correlate failure injection events with monitoring data to understand the impact of failures on the system. Example, integrating with Prometheus, requires pip install Prometheus_client. To run this *. 1 pip install Prometheus_client. 2 run Python service_b.py. 3 access Prometheus metrics at http://localhost 8000. Now you can configure Prometheus to scrape these metrics and set up alerts based on specific thresholds. For example, you could set an alert if the service_b_request_latency_seconds is consistently above a certain value. Considerations and best practices Start small. Begin with small scale, controlled experiments in a non-production environment. Isolate environments. Ensure that failure testing in one environment does not impact other environments. Minimize blast radius. Limit the scope of the failure injection to minimize the potential impact on users. Communicate clearly. Inform stakeholders about the planned failure testing activities. Document everything. Thoroughly document the experiment, including the hypothesis, failure scenario, results, and any actions taken. Automate rollback. Implement automated rollback mechanisms to quickly revert to a stable state if necessary. Security. Take security considerations into account when designing and implementing failure testing strategies. Don't expose sensitive data or compromise system security. Ethical considerations. Be mindful of the potential impact on users and avoid causing unnecessary disruption. 6. Conclusion. Failure testing is a crucial practice for building resilient and reliable distributed systems. By proactively injecting failures and observing how the system behaves, you can identify weaknesses, improve system resilience, and foster a culture of resilience within your organization. Netflix's pioneering work in chaos engineering has demonstrated the value of this approach, and their tools and methodologies provide a solid foundation for implementing failure testing in your own applications. Remember to start small, automate where possible, and continuously learn from the results of your experiments. This continuous feedback loop will lead to a more robust and reliable system.